We continue our discussion by looking at a few questions from the textbooks. So this is question 3.1. Reconsider the problem of co-ed flow between parallel plate for figure 3.1 for a power law non-Newtonian fluid, which is k du dx to the power of n, where n is not equal to 1. Assuming constant pressure and temperature, solve for the velocity distribution uy between the plates of A n less than 1 and B n is greater than 1, and compare with the Newtonian solution with equation 3.6. So for example, we have this situation, and then we have the u is u over 2, 1 plus y over h for equation 3.6. So and then we have this one, the situation. However, we just focus about the using of n here and how to get the value of this one. So this is the continuity equation. So and then this is the Navier Stokes equation. So I already simplified it like this one. So we could take du dt is equal to 0 because it is a steady flow, and then because the velocity is the gravity is vertically. So we could get rho g is equal to 0, and then pressure is constant along the x pressure. So we take dp dx is equal to 0. So this is if the trick is if you think the pressure is not so influenced, so we could assume that the pressure gradient is 0, and then along the x direction, and there is a velocity changes along the y direction. So about the y direction here, you need to understand that this statement shows that the velocity profile is a curve and with no slip condition. So and then I think so many times we solve this one, so we could simplify it as mu d square u over dy square, and then we separate it like this. We integrate it for the first time, so we could get a constant here. So and then we integrate one more time, so we could get the c1y plus c2. So the c1 here is the constant, and c2 also the constant. So and then we need to add the boundary condition here. So in this situation, it gives us, because it is, maybe we assume that this is the 0. So and then the distance to this one is positive h, and the distance to this one is negative h. So mean that the total length here is 2h, but the coordinate will give negative and positive. So here the velocity is capital U because this plate is moving at certain velocity. However, here the velocity is equal to 0. So and then after we substitute all the boundary condition here, so we could get the value of the velocity distribution as this one. So and then for n is not equal to 1, it is okay for us to show or to start our calculation by using this idea. So it means at the step when we split the term of this one, okay, it is okay for us to have d dy, mean the derivation for the du over dy here is with a power of n. And then you could continue your derivation by maintaining the n here, and then you will find that the final answer is the same. As I said, that the effect or the influence of n here is actually will not change the final equation. So I hope you could try this at home. Now we will see another problem for question 3.2. Consider the axial co-ed flow as shown in this figure with both cylinders moving. Find the velocity distribution UR and plot it for U1 equal U naught, U1 equal negative U naught, and U1 equal U2 U naught. So maybe I'm not focusing on this one. So we try to solve this. Okay, but you need to imagine that we have two cylinders. So we have a one cylinder here, and inside this cylinder we have another hollow cylinder. Okay, like this one. Okay, so this is, we have another hollow cylinder here. So and then both of these cylinder is moving. So mean this cylinder also move. So and this cylinder also move. So and then we state that this radius is r equal r naught and this radius is r equal r1 for our calculation. So this surface is actually refer to this surface, okay, and then this surface is actually refer to this surface because the fluid is filled in here. Okay, if we have a fluid here, and then the velocity distribution will occur inside this gap. Okay. So this is the continuity equation for polar coordinates. So I hope I will give the continuity equation and Navier Stokes equation both for Cartesian coordinate and polar coordinate in your test and exam. So please understand that, especially Navier Stokes equation for polar coordinates. So it's different from one axis to another axis. So please be careful when you want to use this one. So and then here, because the movement of our object here is actually according to the z axis here, so means that it is maybe we need to focus on the Navier Stokes of z axis. So and then we could simplify all of that. So for sure we simplified because the flow is steady, so we could cut the value of dt here. So and then because the velocity is actually not moving according to r axis, so we have the ur is 0 here, and then the du is duz. Okay, so mean du okay, duz over d theta here, we got this here, so it means that we have a situation here. So u means the velocity to the uz means the velocity at this moment, at this direction. However, du d theta means the changes of velocity according to the tangent of this one. So because we assume that all the velocity is actually the same, so means that the changes is 0. So at the same time, the du dz means the velocity on the x-axis, on the z-axis here, because it is steady, so means that the velocity here and here on z direction, so this is the z direction, is also 0. So and then the gravity is 0. So and then we have the d rho dz because we assume that normally in a moving cylinder there are no pressure drop. For fluid flow inside a pipe, so maybe we could consider a pressure drop, but here they are actually the moving cylinder, so we assume that dp dz is 0. And then okay, so for this one, again, duz d theta and duz dz is equal to 0. Okay, for this term, we assume that duz dr means the velocity for z direction here, but in term of radius direction. So means that maybe the velocity at this point is different with the velocity at this point. So means that you could imagine, so we have a cylinder here. So this is the r-axis. So mean this is the fluid here. So and then we could assume that the velocity at this point and this point is actually different. Okay, so now we already simplified the value, so we could get this one, and then what we need to do is again, okay, we need, because it is equal to 0, and then we need to integrate them, integrate this equation twice. So for the first integration here, so we could get the constant C1 is equal R du dr, and then we integrate for the second time, so we will get this term. So and then if we integrate the LR 1 over R here, so we will get ln. So the final equation that we get is UR is equal to, so we have equal here, UR is equal to C1 ln R plus C2. So we substitute the value here. So we need to determine the boundary condition according to our object, according to our system. So according to our system here, so we have R equal R naught, and the velocity is U naught, and the R equal to R1, so the velocity at that point is equal to U1. So we substitute the boundary condition, so we will get this term, the amount or the value for C2. So and then okay, so this is about the from the equation. So we have two equation here. So and then we can get the value of C1 and C2 as this one. Okay, so this is the works here is very long, so I just shortcut it. So we could get that the C1 ln R plus C2, so it is equal to U naught ln R over R1 over ln R naught over R1, and so on, as shown in this slide. So means that the idea is very simple, but when we try to solve cylindrical polar cylindrical condition or with using polar coordinate, so might be the mathematical expression will expand. So this is another example using the polar coordinate. A circular cylinder or radius r at steady state rate omega in an infinite fluid of constant rho and mu, assuming purely circular streamlines. Find the velocity and pressure distribution in the fluid and compare with the flow field of an envisaged potential vortex. So here, because it is about the potential vortex, so vortex mean the rotation or the circulation. So means that we have z-axis here, and then we have a vortex, means that fluid which rotate the fluid the cylinder here, and then we have the flow, the r-axis here. Okay, because it says that a circular cylinder or radius r is rotating at a steady angular rate. So means that we have a cylinder here, and cylinder here is rotate at certain speed. So mean if we have gap here, we assume that the fluid in between these will also influence with the rotation. So it will rotate at this direction. So this axis is theta. So we need to use the idea of Navista equation for theta axis. So and then we could simplify everything. So it is a steady du dt. So the velocity of ur is equal to 0. So we neglect this one. So the gravity is not influenced. It's not work there. So and then because it is a constant rho here, and also the so and then we calculate the and then the pressure here dp d theta is equal to 0. Here the question asks to find the pressure distribution. So how we could neglect the value of pressure here? Again, you need to understand the word of dp over d theta. So means that if we have a circular and here, so and then we need to find means at theta angle mean on this path. So this is theta. So the velocity, the pressure on this one will remain constant because it has same velocity actually. Okay. So and then if you have another theta, for example, another track here, okay, so maybe the different here, the pressure at here and here is different. But to say the difference of this pressure, we need to say dP dR because the changes is on the R direction. Okay. So and then you could see here, so we neglect about this one, this one, this one, and so and then we remain the value of this and this and this. So and then we simplified this one, we could get this term. Okay, so and then what we need to do is we need to integrate twice because we have the symbol of this one. So we integrate for the first time, we get this term. And then we integrate for the second time, we get this equation. So we have C1 R squared over 2 plus C2 equal UR. So and then we put the boundary condition. So the boundary condition says that, okay, here in this question, so they only ask about the one cylinder here and then rotate at certain speed, say, and then this is all the fluid. So means that there are no another solid wall here. So that we need to write as at because this surface is rotate, so means that the no slip condition will occur at this one. So means that the maximum velocity is actually occur at this one, at this surface. And then the molecule which is far away from here, actually it remain static. So that's why we write the boundary condition as r equal to infinity, means at the large amount of R, so means that the U is remain 0. So the idea is very simple. For example, you have a very large pool and then you have a very small cylinder here rotate at certain speed. So you will find that the molecule here is influenced by the rotation, it's rotate, but the velocity here may be 0 because the distance the distance of this one is too big, okay, and then the rotational is not influenced at this point. So another thing that you should know is we are talking about the rotational, so mean we use rotational speed. Okay, so rotational speed normally can be used in radian per second, or RPM. Both of these unit is actually reflecting the rotational speed. However, in our first derivation of the equation, we are using the idea of U, which is the unit is meter per second. So meter per second is the linear velocity. So what you need to do is you need to change the linear velocity into the rotational velocity. So the equation or the relation is like this. So normally I will use U is equal R omega is equal to pi dn over 60, where the n here must be in rotation per minute. That's why we divide by 60, and the r here is the radius, so means in meter. So and the omega here must be in radian per second. So if you see this one, so everything the unit is remains still the meter per second. So we change here U is equal R omega, and then we substitute here. So we will get the C1 equal to 0, and then we have the C2 is equal of this one. Okay, so and then to find the pressure, we use the R momentum equation. So we have the du d theta, we have the u naught over u square over r and so on. So we simplified all the things here. Again, the gravity is 0, and then you could understand why everything is 0 here. So we have this term. So and then we change into this one. So because we only have one term of differential form, so we just integrate it once, so, and then we could get these terms. So for sure, after integration, so we get the constant. So we need to calculate what is the value of constant. So we put the condition. So here in condition, we assume that at R equal to capital R. So, and then the pressure will go into P naught. So this means that if we have a rotational cylinder like this, so and then here all there are a lot of fluid around the cylinder. So at point near the cylinder here, because the cylinder is moving at certain velocity, so means that there is a changes of velocity, so maybe there is changes of pressure. So however, at the very far away here, so again the velocity is equal to 0, means that the pressure is remain to atmospheric pressure. That's why we put P naught here. So and then we could rewrite the equation. So and then we could have these terms.